I started this in 1999 with some students. I've been working on restoration in Iraq, the Mesopotamian marshes, working for almost 13 years on restoring the Everglades. And I decided, why not do restoration in my backyard? And so I actually started working on thinking with my students, and we noticed that the water quality in the city of Durham was pretty poor. All the streams coming into Durham were not in too bad shape, and all the ones that left Durham, 5 of them were all in terrible shape. And then you don't have to go very far in any urban system, and you see streams that are cut down, sediment going out, really a big problem. So I got the idea that basically with my class, we'd start designing this, not knowing much about stream restoration. I'm not a stream restoration expert, but I quickly teamed up with people like Will Harmon and Kevin Tweedy and a number of others who are, but I knew my main goal was to basically restore ecological functions of the landscape. So I'm going to give you a bird's eye view of the swamp project, and then we'll go into more detail, but I'm going to really cover the whole integration of this watershed approach. And the state bought into this after they realized, after spending a lot of money on 2,000 feet in Bertie County, and 2,000 feet in Durham County, and 2,000 feet in Ashe County, and then not finding any great results in terms of what they were hoping. That section was okay, but upstream or downstream, were you actually getting any benefits? And so my idea was, as an ecologist, as sort of an ecosystem ecologist, we need to do a whole watershed and look at that. So that's the way I tackled it. So we obviously know why do we want to restore these in the landscape, but this is sort of my beginning view. Obviously, we got a lot of problems with degradation of streams, loss of functions, which is my concern, and then we have all these conditions. We know about incised channels, free-falling, erosion, the non-native species invasions, loss of landscape diversity, and poor water quality, which are a whole bunch of problems, to say the least. And these are actual pictures of some of the students on what some of our streams look like, actually in Durham, but also on Duke Forest. You see the forest, which is overgrown now and grown back since the early 1900s when we bought most of it. Most of the Duke Forest, which is about 10,000 acres, was purchased during the Depression, when land was selling for 25 cents an acre, but nobody had a quarter, except the Duke family, who sold cigarettes at 5 cents a pack. And there were a lot of people smoking at that time. So here you can see erosion, loss, and sediment. Can you all see all right? Are these all right? Okay. And then we have stormwater concerns. You see a stormwater pipe here. We have all the runoff from the cities and all the things that come into these systems. We have that problem. And then, of course, nutrient inputs, fertilizers from playing fields off the Duke campus, residential lawns. We even have occasional sewer line spills. And then, of course, off the highway, which like examples up here, we have urban runoff of everything from what comes off rubber tires, petroleum products, and even some metals in some of these streams. So we have a lot of issues to deal with. And then, of course, we have a huge amount in this area of non-native species, everything from Japanese honeysuckle to Chinese privet, a whole host of species that are non-native to the region. So let's take a look at this in a big, broad context and then focus in on the ecology. So I was mentioning we're in the Cape Fear Basin right here. We're actually located here in Durham. And you can see, obviously, then that this runs from this region all the way down to the mighty Cape Fear. If you look at Upper Sandy Creek watershed, it's about a little over 1,360 acres, 550 hectares. It's a mixed land use. It's an urban forest, mixed setting, but it has 21% roughly of impervious surface. You can see the drainage system here in general. And where we're focusing, where swamp is located, and it stands for Stream Wetland Assessment Management Park, which I got the university to dedicate a few years ago in 2007. As our provost said, I've dedicated buildings, football stadiums, but never a swamp. So the university has dedicated this region as a education and research area. And if you put this in full context here, you can see the whole watershed here, and you can see where swamp sits here at about 24 hectares, and you can see Duke University at 341 hectares here. So Duke University's campus itself makes up a big part of the upper part of just this branch. And of that, if you look, phase 5 is not shown on this, but you can see phase 1, 2, 3, which Eddie talked about in phase 4. What I want to point out is why we have that 21% impervious surface. You can see high density. We're surrounded by the city of Durham, and Duke actually owns a lot of this, actually owns almost all this land at this end. And this, I'm giving you several maps here for context. Here you can see the swamp treatment boundaries. Again, what you can see now, you can actually see that Duke actually, this portion of the campus is actually treated by the Sandy Creek. This other portion of the campus is not, and we'll talk about that briefly. Duke is actually spending money now on its own to treat that part, and we'll work on that. Here you can see on this part here, this is about 200 and some acres of impervious surface in this region alone. So that's giving a large portion of the runoff for the system. So now, Eddie talked about these phases, and I'm going to go and show you. Phase 1, the stream restoration, was here. Notice there are two big branches of Sandy Creek. They're both called Sandy Creek. We have phase 1 here, phase 2, which is our dam pond, phase 3, which is the treatment wetland cells, which are there, which comes right off the Duke football stadium. It's there. Reach 4, 1 and 2 are here off this section of Durham, and 5 is right here, which is the stormwater pond, and then the last phase, which is it's been approved, but not money has not been released, will finish all the headwaters of this entire branch. That was what the state was buying into. That's what we believe will result in being able to take care of the water from this massive part of it. So, if you look, I think the pointer's about dead here, but here maybe not. Keep in mind, there's the football stadium. Keep in mind this curve of the road. This is a key piece to most of these pictures. This is what it looks like from Google. And you will notice also there's some, looks like what they are, sand traps. This is a golf course right on the edge of this project. Now you overlay this, the 5 phases that are done, and you can see where they sit in this context of the campus and also the city of Durham. And I want to only point out, this is from another firm, Eco Engineering, that is now working with Duke. This red is the area that's the last piece to be done in our project, what I call the swamp project. You'll notice a couple of other areas up here and also one over here. The university is going to build, oh good. The university is going to build a large stormwater pond lake up here. And they're going to do this on their own. So let's look at some pictures. This is the pre-construction. And again, you look at this curve. And you look at this field right here. And everything we're going to take a look at is going to be in this region. So this is 2002. And so by 2005, it took us several years to get the permits. We were very close. It took us quite a while to get a number of permits. You can see phase 1, barely in here, and phase 2. And again, there's that field, and here's the curve. So phase 1 and phase 2 were implemented. And 2006, you can begin to see that, in fact, this dam area, this is a jogging trail. This has been put in place. And you can still see that, in fact, that some of the trees have been removed here. And phase 2 was about 75% completed. By 2007, phase 1 and phase 2 are completed, and phase 3 was established up in this region. And again, this just shows you a better picture. Now, for me, they're not very clear, but you can see these all right? Okay, you have. So this is sort of an oblique view. Here's the road, that curved road. Here's that field. And here now you can see the reconfigured stream, which we'll get to see this afternoon. And you'll notice, of course, the vegetation is here. This has been put through this forested area, and new floodplains have been reconstructed in this area, which we'll go through. And also you can see that phase 3, the wetland treatment cells, are now visible on this. Here's a close-up, actually, of phase 3 online. I'm showing you these pictures because you'll have a hard time getting some idea what these are like when you're on the ground, and especially if they're overgrown now. You can see a weir set up here and a stilling pond here, and there's a pipe that comes out underneath the Duke campus right here. So there are the 6 cells actually sitting in there just after they were established. So now by 2010, 1, 2, and 3 are fully operational. The reason I'm going through this is I'm going to switch to the data and the results and what we're doing and what they look like on the ground. And I wanted you to get well into your head what happens, because it's the phase in of these that really makes the difference. Because after phase 1, we didn't have very, as you'll see, the results are not too impressive. In phase 2, then 3, you'll see what happens. Okay, here's an aerial view then of the phase 2 stormwater wetland impoundment. And now in 2010, you can actually see a Ludwigia species growing around the edge here. It's fully operational, and it's flooded fully, and basically is receiving water from the restored wetland streams up above. This shows you by 2010, now you can see the wetland cells. You can barely see them, they're here, but they're now, of course, fully vegetated. So just to finish up with this overview then, and not to beat it to death, but we basically have these phases: 1 here, 2 with a dam, 3 up here, the swamp treatment, 4 the 2 reaches, and then this part is yet to be finished. We have one piece right here that is finished. But you'll also notice something about Duke. This says this is actually Duke's proposed water reclamation and stream mitigation exhibit. Duke has now bought into this. That's probably my most pleasing factor, is when I started this, people thought I was kind of crazy, especially my colleagues, to be doing this on a university campus. University campuses are the worst. We're usually falling behind in terms of air pollution. We're usually falling behind in terms of water quality. We should be the examples. And when we surveyed 1,500 universities, most of them haven't done anything with their water. They say, oh, we have a wastewater treatment plant. That's not the question. The question is, what are you doing with your campus water? How are you treating it? What are you doing with it? And Duke is, I think, actually, I can say, with the exception of a couple, is sort of leading the nation. We've basically got a smart house here with a BMP bioretention. We have all the new structures are to LEED certification. We also have stream mitigation, either or BMPs, on every aspect of the campus that's going in now, so that we're not only going to be sort of carbon neutral by 2020 is our goal, we're going to be sort of blue neutral in a sense. We're going to try to basically treat all the water we can treat. All right, so those are the phases. So let's take a look at what we can look at in these restoration phases, and let's take a look at stream 1. And Eddie showed you this briefly. All right, we start with this. This is what they looked like when we started. And there's the old stream configuration taking a really hard turn here. And as we turn that bend, here's some of the pictures that Eddie showed you, what it looked like. This is in May of 2003. And so let's go into the restoration. This was a priority 1 restoration where we basically built a new channel. We basically buried the old channel and move this. We had enough room to move this and create a new channel. And this is just a very generic sort of goal we set for design criteria. We actually fired the first engineering company because of what they had proposed. My students didn't like it because everything was going to be total stone riprap. The whole thing was going to be all stoned in. It was going to be very stable. But we wanted more native approach, more of a natural systems approach, sort of natural design where we used materials. NC State was working on this, Will Harmon, Barbara Dahl, some other people, so we borrowed heavily from them and actually used their skills. And we basically set some basic designs, and this is just sort of a general one. We'll go into the details of what those were. But obviously we're not going to have streams that are going to be 9 feet or 10 feet deep or 3 meters deep. And we're going to basically try to get some return of at least once every 1.6 years on over the floodplain, create some pools and riffles, and utilize sort of a reference reach approach. And then use some of Harmon's and Dahl's regional curves along with some other things to design what would bank full be. And I'm not going to go into the design, but I just wanted to give you a little bit of background on that. What the discharge should be, what the size of the watershed. So it was designed on natural system design. Will's here and go into great detail on that, as is Kevin Tweedy. So let's look at the new configuration. So the new configuration by June of 2005 looks something like this. And you can see essentially we've done some replanting here to cover this with grass cover. And you can see root wads on this side here. You can see actually pools and riffles being set up. This was removed later. This is actually going through the forest itself. It's another shot in 2005. By 2007, another brand, you can see clearly the pools and riffles that were placed in here and some of the meanders. But most of the native vegetation was left. By 2010, this is a tree that actually just went over on its own, which is being left. And when we get out there, you're going to see this is even now really difficult to see because this stuff that was planted along the riparian shore here, banks are quite overgrown by now. All right, if we take a look at phase 2, here in 2005, you can see this is all forest. This is a big bone of contention for some people. This is a jogging trail. And this jogging trail basically went through the forest, and people were quite upset that this pond, this stormwater pond was created. But to stop the flashiness, we actually got permission to actually put this in for research purposes because we can raise and lower the water 3 feet on this weir system that you'll see. So we can affect the stream back here. We can affect the floodplain. We've been doing studies on how much water should you be allowing in the floodplain, how much can you change that, should you allow overbank flow.
This is upstream of what you showed us just before now?
This is phase 2, it's downstream. This downstream. If you go back and look at that figure, you'll see it's at the bottom. This is the outflow to swamp. So, yeah, please interrupt me. So here's what it looked like in 2007 just as we basically took us about 2 years to get this completed. And the ducks had already moved in. By 2008, this is early, in 2008, you can see the leaves have it's not leafed out yet, but you can see what this system looks like. And the swamp streams that are restored are back this way, and the water is flowing this way. And then by 2012, we've got a number of species that have come in and some we have planted. So we've got a pretty amazing looking system as a natural system. You'll also notice these banks up here, which we'll see, look very wild. People write to us all the time or call us and say, you should mow this and make this nice grass system. This is in the forest. We want to leave this natural. And there's many native species. This dense vegetation also keeps out geese. We do not want thousands of geese in this pond. We have them in other areas. It is. We get a few, but they can't get up on the shore, and I don't know, they're worried about predators, what the biologists tell us. They can't sit up there, so they have a difficulty. They can land on the pond, but they can't really do anything else. We get a few. We have some other ones on campus where we get hundreds.
You all keep trees off the embankment.
We have to keep trees off the embankment, right. They come in, and those have to be kept. Our treatment wetland here, just to show you what it looked like in the design, we started out and this is a stone weir, and we put this in initially, and you can see that the flow, this all comes from a pipe that you'll see right here. This all comes from a pipe, and we basically designed this. This was an interesting system that Will and I struggled with. This system was to treat about 57 acres, I believe, from mainly the campus and mostly fertilizer off the football, soccer fields, and so forth. It's our worst water quality on that region. And we had a lot, we'll see, this is called an offline wetlands because by law, EPA does not allow you to put a wetlands in line, even though it's a pipe. They said it's the stream waters of the US. We had a long argument with EPA in Atlanta, and I asked the question, so you would rather have poor water quality, even though this is just coming from a pipe, and rather than doing this right, and that is make the whole valley a big wetland, treatment wetland, and then let it flow out? And she said, basically yes, we have to have that. We cannot turn over waters of the US. So essentially what we have is a system, as you will see, and I'm showing you with these figures, you'll see them in the field, but it's easier to show here. So we basically low flow, these are flashy, as you can imagine, because it's coming off from fields and some parking lots. When low flow goes down this channel, when high flow comes, essentially what happens is this weir that's here, basically the water comes so rapidly out of that pipe that it flows into these cells, and one cell leads into the other. And so we get the stormwater flow into the wetland cells. That's the way we got around that problem. So technically they're not in line because there's a berm here, but they get the high flow that we want. And that was a way to get around the problem rather than making one big wetland. We did lose some efficiency in that way because we have a lot of berms and less wetland area. Reach 4, which was shown earlier, you can see what it looked like. Here's what it looks like now after restoration. So it looks quite different. And here was the Reach 2 that Eddie showed. So I won't belabor that, but I wanted you to have these pictures. Here's what it looks like within that first summer after restoration. You can see again, we maintained the forest. And what's interesting is, as I say, there are homes on both sides of this, and then Duke owns basically most of this land. Now, phase 5 is an interesting case here. You'll see this pipe and you see all these stones. The city, this is a highway right here coming to this side. This comes underneath the highway. The highway was basically being eroded away, eaten away. And so what we did was we basically proposed that this would be, put a treatment cell in here. This treats 7 major parking lots. This is mainly a stormwater treatment system. And you can see that the banks are eroding. It's basically falling in. It was in pretty bad shape. Each year the city of Durham came as the road was eroding and they just dumped a big pile of rocks in there to kind of prevent it. It was not working. So Eddie showed you this picture of what it looked like in August of 2012. Here's what it looks like as of last week. That pipe has now been stabilized. The bank is here. And here is the holding pond, the front one, which basically then flows into the second one, and then into the third wetlands treatment cell, and then out of that cell into the creek that basically goes back into the stormwater project.
So these cells lower stormwater flow so that you don't re-erode the stream below it?
Correct.
Okay.
And also try to remove some nutrients in these wetland cells.
And you reduce the flow in those streams so that, I mean, you still have a silt bottom, just fill it in with dirt, or you put something more durable in there so that it just can't erode right back down.
In the ponds themselves?
No, I'm talking about in the streams below the pond.
Yes, but the rate at which they come out of these ponds, we can control with baffles, and we can slow that down considerably.
Okay.
So we can hold, this was decised, we can hold a good storm, a really good storm. And so we've shut that down probably by 50% in terms of the flow rate going out of that. But then immediately below, which you'll see in the field, the stream has been armored a bit just where it comes out so that it won't erode immediately.
How about the bottom?
The bottom actually ends up going into the Sandy Creek area, which is not finished. So it's right now it's a little bit more vulnerable because that's the phase that's not finished. That will have to be set up so it will not do what you're talking about. At the moment, that's why we were really waiting for those funds for that part. But that what we'll have to do is to stop that water from. That's the main thing with these urban systems, to stop that massive flow.
Yeah.
Well, that is the overview of the whole project in terms of what was put in place. It's not the design. We have the people here talking about the design. And when we take our breaks, and then we'll have a chance when we go out in the field, all of the engineering plans for each of these phases are there, and you have in the back of your book the 2-page designs for phase 1, and these are all the designs for all the phases that were put in place. So what I want to go through now is actually the ecology. What are the results of putting all this in place? Which is really more of my forte if I have one. So looking at sort of structural and functional responses, and the states, the Clean Water Trust, because of the state legislature and so forth for years, and a lot of these projects forbid monitoring or research, basically. And so the legislature, I don't know if they wanted the information or didn't want the information, but after a while, people began to ask, are we getting any results for the amount of money we spent? Clean Water Trust alone had $100 million a year. It led the nation in terms of monies to do things. That is not the case today, but so let's look at the groundwater functions. What happened in this system? We look at the groundwater functions. Did the stream restoration result in hydrologic conditions to support adjacent wetland functions? Are hydrologic conditions conducive to wetland plant establishment, survival? And what's the role of restored wetland hydrology on some of the functions? You'll be getting more of this when Dr. Flanagan talks and some other people, but. So one of my PhD students, Jen Morris, shows her, we have a whole series of water wells and piezometers. The stream is back here, the restored stream, is to look at what's the influence after a storm. We have a bunch of automated water wells there to try to determine whether the system itself is actually hydrologically functioning as a wetland. So if we look at something, the first thing I want to mention is you'll see this is the restored stream. And what I did is I put in a series of what I call benches. I actually had the construction and the design made so that these areas are low benches and high benches. I actually created terraces that a stream should normally find in a bottomland in some of these areas. But I actually created these 15 centimeters lower than the upper areas to try to create a diversity of microhabitats. A number of restorations, you make just holes in the system to try to do that. I did this on a much larger scale, which you might find in a typical floodplain, to see what effect that would have. So I've been doing this for a long time here. This you can see in 2001, this is the rainfall pattern. The restoration took place here. We were actually doing the pre-monitoring with these wells, the groundwater, and this is the 30 centimeter sort of, this is the surface. This is 30 centimeters. This is what would be legally considered, quote, functioning wetland hydrologically, in a sense, for 2 weeks during the growing season. You can see for large periods of time that in fact we were not anywhere near the surface. This is pre-restoration. There were 30 centimeters way up here in that purple line. We were way down here, 1.5 meters below the surface most of the time. We did have, of course, some drought periods in here, but the point is, most of the time, especially during the growing season, we were sitting well below because the streams were 3 meters below the surface. So we went to this restoration, the first phase 1, and we start to see that in fact this is now sitting for a long period of time up above that 30 centimeter line. And if we just take a typical year, 2008, here we can see March to May, and if you look at March to May, here's that 30 centimeter line, and you can see in this area here, this is one of our bench areas. You can see we're right at the surface or just below the surface. We're well above that. So we're keeping, hydrologically, these are pretty wet compared to where they were. And that was this site over here. If you take a look again at some of these other ones, low bench or high bench, here you can see a high marsh bench. You can see, again, this 2008, you can see that we're sitting, water is right at the surface during that period of time. So when the stream is flowing, this is now not 3 meters deep, it's only about 1 meter deep. We're getting water out over the floodplain. Here's a low bench, and you can see that the water again is basically even higher. Here it's sitting at 10 centimeters, it's basically wet. And in fact, you can see a picture here. Here's the low marsh, low bench on one side, and here's the higher one on this side. It doesn't look like it, but there's a 15 centimeter difference. And this is all natural cattail that came in. We didn't plant this, it all came in. This is a variety of species we planted as an experiment, so I'm not trying to tell you that was a result of being higher. But I'll show you some natural areas we didn't plant, comparing low bench and high bench, or high marsh and low marsh. So let's look at the plant community responses. If we look at the plants, A, B, C, and D, Dr. Ho, who's in the back of the room, worked very carefully on this. He's our plant ecologist. And essentially, we went to these areas. The stream is here. This is the restored stream. Here is our phase 2. And we went to see, these are unplanted areas. What comes in over a period of time now on these areas? And first thing is to match this a bit with the hydrology. And all of these water wells with circles on them indicate they meet the hydrologic criteria. These have water at the surface or just below. And this is our B plots, this is the A plots. And you'll notice all this floodplain area, even far back from the creek, all of those are pretty much meeting the criteria, as are these. The berm area, which you find next to the creek, these are not. These have not met. In other words, it's a bit higher, and these are very sandy, and these have not met the criteria, but this area is. And so we did 5 years of vegetation plots in these areas. This is Mike Osmond, one of my doctoral students. And this is sort of the summary. This is coming out in the paper in 2013. This is fluctuations of plant species in the high marsh. And what I want you to see, starting in 2005 to 2009, is in the high marsh, there appears to be, and these are A plots, B, C, and D, there's a decrease going on. That decrease is actually upland species dying out. In the low marsh, you can see a slight increase going up, and that is wetland species coming in. The paper describes what those species are. So in the high marsh, we're losing species, but we're losing the diversity of upland species, and we're gaining in the low marsh wetland species. And in fact, if you look now, we usually have wetland species coming in both, but the highest diversity was here. The other interesting aspect of this study is if you look at the high marsh and the low marsh, one thing that we really have a problem with in almost all of our studies around here is microstegium, which is an invasive species. And one of the outcomes of this particular study was that in the low marsh, if you kept the water levels, this is the wettest system by far. These two here, the A and the B, were the wettest. They all were wet. Basically, microstegium did not come in. So the difference of about 10 centimeters of water, or just below the surface, kept microstegium from taking off on us. Whereas all the other plots, at least the understory, we had microstegium coming in, which is a problem.
Did you just say if you make it a little deeper, there wasn't microstegium, or if you made it shallow water?
Either shallow water, or we just cut the bank down a little bit so that it overflooded more. Either way, you could do it either way. Now, I usually joke when I gave this talk before, say, I'm now going to give you great detailed studies on all the plants that moved in. There was 108 species, and that's all I'm going to say. We have about 108 species. Dr. Ho's, maybe numbers changed slightly, but he put that together. That's sort of that's the diversity of plants that now exist in that whole swamp area, which is amazing. It's probably tripled from what we had before.
They came in by themselves.
Most of these, yes.
They had seeds that had
Found with birds, all sorts of things, you know. The habitat was correct.
Were there any endangered species?
Any other endangered species list?
Not at this point.
No. But many which had not been seen in the forest, we had some that had not been seen in this area. They weren't there at all.
The habitat is surrounded by urban areas, so there are many introduced species coming in.
So we have some invasive you're talking about?
The introduced species.
Introduced.
Species.
So we have a number of the native ones. We have a few non-native ones. So we'll talk, coming up after we have our break, on functional uplift. And really what I'm talking about, which fits into his concept of functional uplift, are some of the information he keeps asking about. because there's a big argument whether or not, in fact, you do this geomorphological restoration, you do this. Some people argue, in fact, okay, you got the geomorphology, but you don't get any ecology. You're not getting anything. It's not going to be working what you want. And so a lot of the ecologists are really not, there's been big arguments. We've been to workshops. Barbara's been to some, I know, that's been, we're not happy with this because we don't think it's giving you ecological services. So I just threw in that functional uplift to say that we'll talk a lot more about that, but does it improve habitat for macroinvertebrates? Well, this is a study from Jean Still, somebody,
That was my coworker.
yeah.
She is,
So she's working in, in Virginia, where?
Virginia Beach.
Virginia Beach, yeah. And here she was doing her master's work, which is basically doing the kick sampling and doing all of this. When she came to Duke, she said, I don't really want to do macroinvertebrates. My mother is an entomologist, and I want to go to some different area. But in the end, she said she was drawn back into it because she knew so much about them. And actually, I think she liked it a lot more than she thought. So in 2005, just as we were doing this, I had a study in 2001 done to see how many taxa were in Sandy Creek. It was 34 taxa. And then in 2005, I had another master's student come, and you can see the comparison of 2004 and 5, and these are the invertebrates. And the point is, we jumped from 34 taxa to 89 just after we put this in place. It was just a huge burst. But even in 2004 and 2005, you can see the difference between the red and the green. We're getting quite a shift, an increase in some of these things like Diptera, the flies, and the gastropods, and Odonata, which are the dragonflies and so forth. But then by 2009, when Jean did her work, much more detailed, because she was a really good entomologist, we look now things at like gatherers, filter feeders, predators, shredders, scrapers, all the things that make stream macroinvertebrate people get really weak-kneed, and so all the good things that are in those streams. You can see WT1 is our input, WT5 is our output, but basically the pre is down below in the green, and that's the main thing. We're going down the channel of the restoration on phase 1, but you can see the green, like we had 6 gatherers versus 22 or 20, filter collectors 30 versus 4, predators 32 versus 23, shredders. The numbers have just gone way up in terms of this. This relates to what I'm going to next, is the water quality. And then you can see MC, which is Mud Creek. That is the reference for this region. And so we're basically reintroducing these back. And for my other grad student here, I'm using Scott Winton and Randy Nybarger, who are both great birders. Last minute I said, we don't have anything on birds. This isn't fair to not have anything on birds. Scott would shoot me. So basically they've been doing bird surveys for 5 years, 4 years. You have, Randy.
Yes, it's 5 years, I think, Scott, isn't it?
So this is in the book, and I won't go through great detail, but the point is we're actually probably triple the number of bird species that are using this habitat because, of course, we've created new habitat from what we had before, and they're doing winter and summer surveys. And there's the list, and I won't, obviously you can't read it in great detail, but and then we go out there, we have a number of birders who go out there now because of this. So that's a large list, to say the least. And so when we go out and see the trails, we actually have part of our educational trail system, all of these types of signs out there that indicate some of the species that you'll find. So conclusion of this part, the macroinvertebrate community was restored, the plant diversity increased in the low marsh, the diversity decreased in the high marsh for the reasons I mentioned. We had invasive microstegium did not invade the low wet benches. The stream macroinvertebrate species increased about 3-fold, and the bird species now number over 100. So ecologically, we've made some tremendous improvements in this system, which I think are very much possible.
What was the primary difference between your restoration that caused a 3x improvement in macroinvertebrates and many others which have failed to increase any number of the diversity or the number of macroinvertebrates? What did you do that the other restorations didn't do?
I think there are 2 aspects. We can't prove it, but one, I think creating the pools and riffles and creating some of the some of the changes making the habitat. But number two, I think improving the water quality in the stream, which is the next part I'm going to mention. I think we got some of that. You have to have the water quality. Some of these, the macroinvertebrate specialists will tell you, you do not get certain species unless you improve that water quality.
And what about you control the flow of water that goes through there too? Or is this an area where you haven't controlled the flow?
We don't control the flow coming into those parts of the streams. They come in, except for the stilling wells and upstream a little bit. Yeah. Now we have slowed it down, we've stepped it down, we've oxygenated the water in some places, we've created some pools, we've slowed it down, we've done that for sure. And we are also removing a lot of sediment, which I'll get into. So I think we've improved water quality and we've improved the habitat. And when we get out there, we can actually see some of this habitat. I think that's one of the big things that Will's talked about in terms of, and Kevin, about how the habitat, you just can't have a straight race through the whole system. If you don't, you can't have, and also, one of the things that's helped, we've got a lot of organic matter in the stream now, which we didn't have, which gives them something to eat. You need organic matter in that stream. We've got logs, we've got other materials, we get leaves falling in. A lot of the restoration you see, like in open ag fields, they've got the restoration there, but there's too much sunlight, no organic matter. Okay, now we get to the part that the state really is interested in, probably, I'm not saying they're not interested in the other aspects, but this is a part obviously a lot of people are interested in. Does a stream and wetland restoration result in improved water quality and nutrient retention? So I'll show you some early data and then I'll go into more detail. These are our water sampling stations. And we've sampled down the stream inputs, and then this is our output. So we have things like WT1, BR5. This is off the football stadium where our worst water quality is. So we measured on the 319 grant, which got us started, a host of things. I'm not going to hit you with all those. That report is available. It's on our website, which you can go and download a lot of these reports. They're there. They're free. You just download them. And this was a very detailed 3-year report on these 11 stations for all fecal coliforms, temperature, BOD, turbidity, the standard nutrients, and then all sorts of cations. And then we did storm events and so on, and we've done sediments, as you'll see. So just to give you a picture, 2 years after, here's an ambient March to December, just to give you some idea of concentration. This is phosphorus. Coming in off, this is that curve again. Coming in, we have 377 parts per billion or micrograms per liter. A typical ambient stream in the Piedmont, according to EPA, should be 30. That's what's considered a good stream, 30. So this is 377, so it's 10 times more. And you can see here, when it comes out, it's 186. So it's not back to 30, but that's what it is as of this 2007. Remember, we've only put in part of the system so far. If you look at nitrate, here you can see numbers that go 943, 168. Coming out downstream here is 68. We're doing really pretty well with nitrogen by comparison, nitrate, nitrogen. Here's the dam. So let's look at the summary of this. So the way the next couple of diagrams work, here's the state of North Carolina's ambient criteria. That's this dashed line right here. And one of the issues is fecal coliforms. And you'll see the red is the pre, and then we got phase 1, phase 2, and phase 3. So what difference does it make after we put in phase 1, phase 2, and phase 3? Phase 1, you can see, or pre, I should see, is the red. You can see we're well above this. And phase 1, we're still above this. But by the time we get to phase 2 and phase 3, we start dropping below. And you can see downstream the reference sites are pretty much always below or just barely touching it. So we have dropped that dramatically in terms of fecal coliforms by the time we put all 3 phases in: the treatment wetland, the and the phase 1 stream. The nitrate-nitrite situation is the same. You can see the line here for the state, and the reds are above this. It's not until we get to the downstream here, until we get down to the phase 2 and 3, that we actually get below the state's considered concentration that they particularly want for that. And you can see again, the downstream reference systems are all below what the state wants, but Sandy Creek was not. Notice BR5 is the football fields and all the fertilized fields. It never gets below the state criteria because they fertilize those fields to keep them green all the time. So we've actually been trying to work with the campus to get them to reduce the fertilizer, because even though I put in 6 treatment cells, it's the back of the envelope told me when we put it in, the valley was too small. Will knew that, I knew that. It wasn't big enough to treat that 50-some acres. It helps, but it's just not big enough to treat that. So I put that in there to show you, but by the time it comes out of the downstream, remember BR5 is a treatment 3. It runs eventually into that pond. By the time it gets to the outflow, the big system, it does meet the criteria, but not the treatment cells by themselves. Is that clear?
Do the treatment cells have, do they have anything in the bottom, like, people have used sand and wood chips in the bottom to try to get
It's filled with vegetation, so it's got all kinds of organic matter in there. So let's take a look at the again, I'm emphasizing the idea of this phased-in system. Look at, we're going to call what we call paired site analysis. Look at changes in the nutrient criteria. And essentially look upstream and downstream, and then the deltas will indicate a change in concentration through the project site. Positive will indicate an increase through the site, and the negative indicates decreases, and the 0 indicates no change. So if you look at this, you can now follow phase 1, the pre-phase, phase 1, phase 2, phase 3. You can see here, if we're looking for paired site analysis on nitrogen, changes in nitrogen, you can see where it is for this. And A, B, and C basically are total nitrogen, nitrate, and ammonia. And you see for totals, it's going down after phase 1, phase 2, and phase 3. And then the B, nitrate, has gone down. It's well below the 0 line here. And then ammonia has actually gone up a little bit, but the totals have gone down. Same thing for phosphorus. You can see phase 1, phase 2, but by the time you add in phase 3, which did help, we basically have dropped, because phase 3 was the worst site, that's that BR5. Even though it's not removing all of it, it's helping a lot. So remember, here's that BR5 is right here. The downstream one is right here. So now let's take a look. That's just concentration. Let's look at the mass balance. So we're going to separate 2 things. We're about to finish up here. We're going to separate storms and we're going to separate base flow. This is Neil out there. I make him go out in the rain. And actually, you know, that's the thing. If it does rain, we'll actually get to see some water flow this afternoon. And this is, you can see that this is what the stream looks like when we actually get some storms and we actually get some fair amount of water in these systems. If we have a hurricane, we can have water up to here. And this is the dam outflow site, which we have pressure transducers, so we can actually, this is the weir that we can raise and lower, which we'll see this afternoon. We can basically control that flow. We can measure it. And so here's a typical hydrograph in say 08 and 09. You can see the base flow here is pretty low. It's work Dr. Flanagan's been putting together here, and you can see the storm peaks are quite, can be quite severe. And we also know from upstream, downstream, there's not much evaporation, especially during the storms. Basically, they're offset, but there's not much evaporation. So the concentrations we can look at upstream, downstream, we don't have to worry about ET. So if we look at the numbers, here's some storm events. Here's the mass balance approach for nitrate, nitrite. Here's what's coming in the main stem. Here's what's coming in phase 3. Again, I told you it's higher. So that's the total sum of the input in this storm. And here's the downstream output. So there's about a 64% reduction. And the same thing for phosphorus. You can see the main stem, phase 3, input, downstream, in the 20s, not so much for phosphorus. because there's still a lot of sediment moving through the system. So that's for the storm events. Now you'll say, what about phase 4 and 5? 5's not complete, and 4, we just are getting the data in now from the antibranching, so we don't have that part added in yet. Now let's look at the annual load. Let's look at a whole year, and this is, I think, 2009, I think, isn't it, Neil?
Yeah, 2008 to 2009 water year.
So basically, if you look at nitrate, nitrogen in kilograms, here are all the tributary inputs, phase 3, WT1, and then we see the upstream sum, downstream, and basically we can see the percent reduction here. So our total NO3, NO2 load, we're getting almost 68% reduction in nitrate, nitrogen coming out of that system. That's this, right, this is blue right here. So that's the difference when you add up all the difference between here and here. That's load in kilograms. If you look at phosphorus, again, the upstream load, the downstream, and then you can see here we're getting about 25% reduction in annual phosphorus load. So conclusions on the water quality part. Water quality has dramatically improved. We've reduced nitrate, nitrogen by 64%. We're not doing quite as well for total nitrogen because there's a lot of organic matter that comes out, I think especially that. Basically, we significantly reduced fecal coliforms and a number of the other ions, which I don't have time to go through today. So we're definitely getting water quality improvement on the system after the phases are in. And the last part will be sediment retention. So we're concerned that when we get these storms, it's called Sandy Creek for a reason, and also this whole area in the Triassic Basin, we get a lot of sediment, especially from projects and things going on upstream in Durham. And this is Eddie's favorite slide. So what we did, one of my grad students, who went on to become a professor at the University of Hawaii, Greg Brulin, basically put this together. This was actually collected upstream and downstream in a big storm. And you can see the color of the water, and this is basically, he went every few hundred meters and basically went down the stream and basically collected the water, and you can see, this is out to the lake, before it, the bottom here, you can see the color, it's getting clearer and clearer and clearer. The sediment has been dropping out of the system. So Eddie likes this because people say, well, what's the proof of the sediment dropping out? You can see it. But we've got other ways of looking at it. We actually measure it in the water. And so this is probably one of the state's concerns. Total suspended solids, we can see influx, outflux, and the amount retained. And we did this, and we can see we're getting about 70% of the total suspended solids, which is, if you look at the tonnage, it's a little over 500 metric tons of sediment that are being basically coming into the system, and then retained about 400. And then that's just looking in the water system, and this is when data becomes scary. We went out and put this is the whole swamp project, and from 2006 to 2010, here's the input, here's the dam output. We put feldspar markers. Does everybody know what feldspar markers are? Feldspar is what potting clay people use. It comes actually from spruce pine, North Carolina, besides other places. You buy it in bags. It's about 100 pounds bags. It's white. It's like a clay. It's white clay. And it looks like sheetrock. When you put it out, you basically put it out in a stovepipe or something, and you pour about this much in, sprinkle a little water on it. It turns hard, like sheetrock, and then sits at the surface. And then once you put that there, you mark where it is, and you put 50 or 60 of these around. You go every year and you go back and you measure the amount of sediment that's built up on top of it. We put it in the bottoms of the lake out there. We put it all over the wetland. And this is a Krieg picture of inverse distance weighted interpolation. And what's really cool about this is you can see the red spots, and you can see here the annual accretion rate in centimeters per year. Right, you expect right when it comes in, that's the big spot, it floods this area. This is all the wetland that we've created, and then there's a few other wetlands in these A, B, C, D, and then this is the lake. And if you put that together, it basically comes out that the riparian floodplain, it's been storing, which surprised us, everybody has asked us, 399 metric tons storage per year of sediment on the floodplain and 89 in the lake. People were telling us, no, you must have made a mistake. You got to flip that. It's all in the lake and it's not in the floodplain. But we've got all these feldspar markers that says it's in the floodplain because we're getting the water out over the floodplain and not in the lake. Obviously, there's a concern that if the lake is going to be filled up, much faster, if it's all going in the lake. So on average, we're getting 488 metric tons. So what we measured in the water, that's what's scary, and what we measured on the land, it's a difference of about 100 metric tons, but it's close. So we feel like we're in the ballpark of the sediment retention.
I had just a comment, I believe that because on our bottom base of the rock range, we have permanent pins that we have to use metal detector to find. Some of them are up to a foot, 8 inches to a foot below the surface of the floodplain now, from so much accumulation
Really?
on that. So if you've got, that's where we have the really wide,
Flood.
100-foot wide floodplain where it's really getting out frequently. A lot of that sediment, that's where it's
Going.
dropping out.
Yeah, and people get surprised by that.
This creates a lifetime for your system, because essentially, you would think that it's going to build up to a point where now it may not come out over the banks, and it's going to end up being inside, relatively in size, like it had been before. Is it 50 years or 100 years?
Good question. We all wonder what it may be, what that period is. Now, one thing is we've noticed that if the construction goes up or down, we had some construction on campus, you're going to see one of our settling ponds, it's virtually full of sediment. It was empty. We had no sediment coming in. We were really happy about that for 4 years. And then they made a huge construction on the campus and they filled it, even though they had their sediment barriers. So Durham, the sections of Durham are not building up that many new things, so we think it was going to take, in other words, we're not a young city in the sense that we're going to be massively building. And now most places that are building are requiring BMPs and requiring this, trying to keep the sediment down. It will, obviously, it's still bringing in 400 tons. It will happen. 50 years, 100 years, I don't know the answer to that. I'll come back 50 years and tell you.
Along these lines of the sediment building up in the floodplain, I've always kind of wondered about the impacts to the hardwoods that were there. Now you're putting a foot of dirt on it every couple of years, for example. Have you noticed a decrease in the survival of the average forest?
You're going to see a number of dead trees out there. Not that many, but you're going to see a number of trees. We cut back some of the ones we actually did by species, like tulip poplar, for example. Tulip poplar like to be on the edge of streams. They like to get wet, but they don't like to be drowned. And they're going to die out, so we took some of those out. A few other ones we've left further back. We've lost a few of those. By and large, they're pretty good shape because so far the water it's not about this much on one tree, and it's kind of spread out. But we probably will have some impact, although these trees do pretty well if it's not a foot in a year.
Right, sort of going back from an abandoned terrace community to a wetland, back to a wetland community.
Sorry, Neil?
The tree community is going from like a dry or abandoned terrace plant tree community back to a wetland community. Because some of those species don't like it as wet as it is now in storage.
Right, but the sediment on the roots are a problem, and I think we probably lost a few because of that. But I think we've stabilized to some degree. Now, what we had, for example, river birch and a few other species that were there, they were really old. They were actually on an abandoned, you could tell they were on an abandoned part of the stream. They had been originally part of a stream before the city changed, put a road in, put a pipe in, and the stream moved over here. So actually, in some cases, those trees are still doing pretty well because they were originally part of a stream complex. Some of the other ones, no. And definitely the upland species, no way. They all died pretty much. We took them out. I think I'm about done here. So, swamp removal, 488 metric tons, nearly 2,000 metric tons of sediment since 2006. The number is kind of mind-boggling. You just don't think it's going to be that much, but if you go out there, as you said, Barbara, you can see just sometimes in 1 or 2 major storms, you can see an amazing amount of stuff. So that's pretty much the ecological part of it. Just to point out again, this could not be possible without funding from the Clean Water Management Trust and the Enhancement Program in North Carolina, Durham Soil and Waters Cooperation, EPA, NSF. Also, I had to convince Duke, I mean, you may think that's a small feat, to convince the administration to turn over lands is not an easy thing to do. But Duke Forest Manager's been great, and the Duke facilities have really bought into this, and they really, and as well as USDA for doing that. So, and obviously I couldn't do all this work. I didn't do it all myself. There's a huge number of people. This is not all of them. But if you go to our wetland site, you will see not only that, and you see in the back of your book, reports. You also see a paper I put in there, which we published in 2011, which has a lot of this data